So like I said, last class we talked about average rates of changes and why we started to develop calculus. Then we talked about limits, but only in like an introductory way, aka like looking at graphs. But not all the times are you going to have a graph or a graphing calculator, so we will be finding some of these limits analytically, which means by hand. So the steps to do this are as follows. We want to try what's called direct substitution, and it is exactly what it sounds like. You're going to directly substitute the limit number into the equation. Because there are times that the limit is exactly what you're able to evaluate. When it's not, meaning if it doesn't work, you will get what's called an indeterminate form. Indeterminate form is just 0 over 0. We straight up don't know what happens when you take 0 and divide it by 0. So when we get 0 over 0, we're like, well, hold on. We need to do something about this. And what we're going to do is try canceling in some way, whether that's by factoring and canceling, using identities and canceling. There's some sort of cancellation that will occur for us to then try the substitution step one more time. After that, if you still get some number divided by 0, maybe not 0 over 0, but like 5 divided by 0, well, you can't divide by 0. What you would then say is that the limit does not exist. So that's when you get a DNE at the end of this, is if you still plug it in and you're still dividing by 0. So sometimes it's as easy as it sounds. Like we are just going to directly substitute the limit value into the function. So if we zoom in on this first question, it says find the limit as theta approaches pi of pi times secant, as of theta times secant of theta. Doesn't matter what it looks like or what kind of function it is. When we are finding the limits analytically, we just plug the number in first. So what we're going to do is we're going to take that function, theta times secant of theta, and we're just going to substitute in pi, because that's what we're finding the limit of. If we start to simplify and find values and this does not turn into an indeterminate form, meaning I get an answer, then that's the limit. So we figure out what the secant of pi is. Prefer that you use your formula chart. So look on your formula chart. On secant, there's not secant in your table, but what is secant the reciprocal of? Cosine. So you can look at cosine of pi and flip the number over. Should be -1? -1. So really, secant of pi is still -1 because the reciprocal of -1 is -1. And what is pi times -1? Great. That is not an indeterminate form. That's a straight up number. And since I got a number, that's the limit. -pi. So sometimes just straight up plugging it in is going to work. So let's try the second one. If I'm asking you to find the limit as x approaches pi over 6 of cosine of x, we first try just directly substituting it in. So we'd be doing the cosine of pi over 6. Can I take the cosine of pi over 6 and get a number? Yeah, what is the cosine of pi over 6? Great, that's the answer. If we were to graph cosine and look at where it is equal to pi over 6, the output would be square root 3 over 2. But of course, it's not always that easy. Because when we try this direct substitution in this next problem, and we plug in 0, it's going to be 0 squared minus 7 times 0 over 0. Cool. What's 0 squared?
0.
What's 7 times 0? 0. So don't I end up with 0 over 0? That's a problem. Okay. We can't tell what's happening at this graph when it says 0 over 0. So what we do is we look for ways to factor, to use an identity so that we can cancel stuff out. I first recommend always looking to see if there's a GCF in the top or bottom. Does this numerator or denominator have a GCF? X. So if I factor out x, I'd be left with x times x minus 7 over x. Right? I just took out an x from the numerator. What happens now? The x's cancel. So I'm just left with the formula x minus 7. Let's take the limit, which means we just directly substitute back in. What's 0 minus 7? Great, that's the limit. What we're doing here is we're getting rid of any holes in the graph. Because right now, if we think back to when we did rational functions in the Rady method, we'd look for things that canceled out top and bottom, and those created holes in my graph. The holes mess up the fact that I can do a limit because it's undefined at a hole. But if I look on the left side and the right side of the hole, those limits are going to exist. So if we get rid of the hole values, which there would be a hole at 0 here, we'd be able to take the limit. I forgot if we had fully done this problem, so was there any more questions about this now that it's after lunch? Are we okay? Silence means we're okay. All right, number 4. So we're going to take the limit as x approaches 1 of this function. Some of you might be able to see what's coming, but when we plug 1 in here, it'd be 1 squared plus 5 times 1 minus 6 over 1 minus 1. 1 times 1, or 1 squared is 1, plus 5 times 1, which is 5. That's 1 plus 5 minus 6. That's 0 over 0. Uh-oh, we have another indeterminate form. So we need to find a way for things to cancel, otherwise the limit does not exist. Is there a way we can try to cancel stuff in this problem?
GCFX?
We can look for a GCF of that numerator. Do all 3 terms have a GCF? No, so what are we going to need to do to that?
Separate them into like x.
Yeah, we're going to have to factor. It's not a difference of squares, but that is something to remember for this. We're just going to straight up factor it.
It's like plus 2 and then minus 3.
So when we're factoring, we're looking for the factors of 6 that will end up adding to 5. Things that multiply to 6 are 1 times 6 and 2 times 3. So we just try it because we're in the guess and check method. If we have 1 and 6, is there a way to combine those to get 5?
Yes.
Yeah.
What is it?
Minus
-1
1.
and a positive 6. Ooh, now that we factored it, what happens? The x minus 1 cancels out, which means this function is just x plus 6. And if we try direct substitution, now that we've gotten rid of the hole, because there's a hole in this graph, this would be 1 plus 6, which is 7. So the limit as x approaches 1 of this function is 7. So again, once we noticed it was indeterminate form, we go ahead and we try to cancel some stuff using some of the algebra skills we have. Ooh, number 5. What kind of function is this? Starts with a P. Piecewise. It's the Frankenstein graphs where we have a bunch of different things all put together. If you notice in this Frankenstein graph, we have a function that's occurring when x is what?
X is less than -4.
When x is less than -4, we have a function when x is exactly equal to -4, and we have a different function when x is greater than -4. Okay, so what we're going to do here is we're going to find the limit as x approaches -4. For direct substitution in a piecewise function, you actually need to directly substitute it into the left side and the right side of -4. This is the left side. This is the right side. Why are these the left and the right side of -4? Specifically with those symbols right there.
Because it points towards the left and it points towards the right.
Okay, well, yeah, so the top one is a less than symbol, which means it's on the left. The second one is a greater than symbol, which means it's looking on the right. So for me to directly substitute into a piecewise function, I'm going to have to substitute it twice. Because I want to check for the first part when x is, or the function is x minus 5. So if we do -4 minus 5, we get -9. We got a number. Fabulous. It's not 0 over 0. And if we try the other one, where it's -x plus 1 squared, and we try directly substituting in there, this would be -4 plus 1 squared. -4 plus 1 is -3. So we'd have -3 squared. What's -3 squared? 9, make it negative. So this right side and left side are the same number. We just defined a limit last class to be what happens when the left side and the right side are equal. Are my left side and right side equal? Yeah, so what's the limit here?
-9.
-9. I didn't have to do anything fancy like I did in examples 3 and 4 because I didn't get indeterminate form. So I didn't have to factor, I didn't have to do any sort of identity. I was just able to directly substitute it in.
Okay, so greater than, equal than signs, that's essentially asking what's x as it approaches the left side or approaches the right side?
Yes, because if you remember about piecewise functions, they have different parts depending on what the domain is. So for this one, we have a linear equation as we get close to -4. Exactly at -4, it's just a dot. It's just constant, 6. And then right after it, we have a quadratic that takes over.
Oh, okay.
But they happen to be going towards the same number at that value, both sides. Mm-hmm.
Would it matter if when it says limit x going towards -4, if there's like a to the right or left, would there ever be like that?
There could be, but when we're doing analytical limits, it's usually going to be the limit itself, not the left side, right side. But I could ask that question. I probably won't, but I could. I feel like you were about to ask a question. No? Okay.
Oh, it's fine, my throat.
Let's try number 6.
Oh, you? Oh, I got scared.
So we want to try always just direct substitution first, which means if we take the limit as x approaches a of this function, that means we're just going to plug in an a. Now we're plugging in a everywhere there was an x, which yes makes it look like a whole bunch of a's. That's fine. What's a minus a?
0.
What's a to the 4th minus a to the 4th?
0.
Oh, we have an indeterminate form. That's a problem. So what do we need to do to try to find this limit? See if anything cancels. The best thing you can do to try to find if anything cancels is look for GCFs or start factoring.
There's a difference of cubes, right?
Technically it's a difference of squares because 4 is still a square number. So this would be x squared minus a squared times x squared plus a squared, since it's to the 4th power. Does anything cancel yet?
Yeah.
No. Can we keep factoring though?
Yeah.
What else do you see is in this problem? Maybe specifically right here. It's still the difference of 2 squares. Okay, let's factor it out again. We're going to have x minus a over x minus a, x plus a, times x squared plus a squared. What happens now?
Cancel.
What cancels?
The x minus a.
X. Yeah, so we have taken care of the hole in the graph. That's where the hole would be. So now that we've factored that out and canceled, we are left with the equation 1 over x plus a, x squared plus a squared. Since we've canceled, we're going to try direct substitution one more time, which I know you don't have a lot of room left, so make it small. What's up?
Can you combine like 1 over x cubed plus a cubed?
If we were adding, maybe, but those are not like terms, and we're multiplying them.
Oh, okay.
But when we plug in the a, so I'm going to come back, I'm going to come up here because I ran out of space, and we plug in the a value again, we try direct substitution one more time. We'd have a plus a times a squared plus a squared. Well, now I have a bunch of like terms. What's a plus a?
2a.
What's a squared plus a squared? And now I can multiply, since those are monomials, one term. 2 times 2 is 4. A times a squared is a cubed. We couldn't do this limit, and I know it doesn't look like a number. We'd be getting numbers for the rest of these problems, but that's because we were plugging in a number. For this one, since we are plugging in a letter, we got out a limit still with a variable in it. 1 over 4a cubed. So we just have to be prepared to try to find things that cancel when we get that indeterminate form. Can we try another? No. Well, we're doing it anyways. Okay, number 7. What should I do first when I'm trying to find a limit analytically? Plug in the number. Let's do it.
Why can't we just like cancel out first?
Because sometimes it will straight up work.
Oh, okay.
So you always want to try direct substitution so you're not doing extra work. So if we do -5 squared minus 36 over -5 squared plus 5 times negative 5 plus 10. Negative 5 squared is 25. Again, negative 5 squared, 25. 5 times negative 5 is negative 25 plus 10. That's a whole 7. I was just looking at my key like, what? Thank you. So that means that's a 35. That's better. What's going to happen in the denominator here? It's going to be 0. And I have negative 11 over 0. That's not an indeterminate form. That's undefined. So what I recommend in this problem is, 1, check your work. Make sure you didn't do what I just did and change the numbers. Ah, look, I did that on purpose. Or number 2, let's go ahead and factor and just check if anything cancels. Can we factor this polynomial or this rational function? Difference of squares, which means the top is what? Yep. The bottom does not have a GCF, but it is a regular trinomial. So we guess and check. X plus 2 and x plus 5. 2 times 5 is 10. 2 plus 5 is 7. Does anything cancel? No. So there's nothing else I can really do with this to find a limit. And since I got an undefined limit, this limit does not exist. Now, if you notice, this next problem is the same rational function, so we've already factored it and nothing's going to cancel. But here's why you always try direct substitution first. If we directly substitute 6 into this function, we'd have 6 squared minus 36 over 6 squared plus 7 times 6 plus 10. 6 squared is 36. And I can tell you're going to panic because you see up there at the top that you have 36 minus 36, which is what?
0.
But what is the denominator? Is it 0? No, it's actually 88. What is 0 divided by 88?
0.
It's just 0. So we didn't have to do any sort of factoring here because when we directly substituted it in, we did have a limit for this function at this point. So it depends on what value you're plugging in, which changes the limit, because the limit can be different across all of the x values for the same function. So we always try direct substitution first, and if it doesn't work, we try to factor and cancel. If nothing factors and cancels, then we're done. Last one on this side. Ah, our favorite. Let's add some trig into it. What do we do first when we're finding a limit? Plug it in. So we'd have cosine of pi over 2 over 1 minus sine squared of pi over 2. You have your formula charts. What is the cosine of pi over 2? 0. What is sine of pi over 2? 1. Now I'm squaring that 1 because it's sine squared. Remember, when we're squaring a trig function, we put the square on the sign. When we're squaring a number, we put the square on the outside. Well, what's 1 minus 1 squared? So we get a what here? What is that called? What I've been calling those? Not a sad face. Indeterminate form. So we have to do something about it. We can't really factor here. But we can notice that this looks familiar to us.
Oh, the tangent thing.
Wait.
Pythagorean identity.
It's the Pythagorean identity. What is 1 minus sine squared of theta equal to?
Cosine squared.
Okay, so if I rewrite this problem utilizing that Pythagorean identity, does anything cancel?
The cosine.
There is a cosine on top and there are 2 cosines on bottom. Which means now this is what? 1 over cosine of theta. Something is canceled. We've taken care of the whole, the reason why it got that indeterminate form. Now we can plug it straight back in. We try again.
Isn't Pythagorean identity? Oh, that's 1 minus
It is secant, so you could have changed that to secant to do this, but our formula chart has cosines on it, so I left it like this. Again, what is cosine of pi over 2?
0.
Oof, now I get 1 over 0.
Oh.
Undefined.
Undefined, so how do you answer the limit?
DNF.
D and E does not exist. So when you're finding limits analytically, first try directly substituting because sometimes it works. If it doesn't work, we find a way for things to cancel. Usually factoring, potentially identities. Yes? Let's go to the back. On the back, we're bringing back something we've talked about before. It's been a minute. We have our vertical and horizontal asymptotes. Now this is going to happen mostly for what we deal with rational functions only. But we've already gone over this but it was last semester. So let's freshen it up in our brains. And we're going to apply some calculus to it. A vertical asymptote is a vertical line L if one of the following limits exist, meaning the limit as x approaches some value of f of x is positive or negative infinity. Meaning, if we look at the graph at a certain point, and the graph is going all the way up or all the way down to positive or negative infinity, then we have a vertical asymptote. So to do this, and we've done this before, to find the equation of a vertical asymptote, we're going to first determine if there are any holes by factoring and canceling. And then we're going to set the denominator equal to 0 to solve for that equation. Again, this is something we've done before. We did it when we studied rational functions. It's just been a minute. So first things first, we factor. How do I set up the guess and check in the top here? 2x in the first one and x in the second one. We're looking for factors of 9. 1 times 9, 3 times 3. That will add to 9. Huh? Well, here's why it's guess and check. So if we try 1 times 9, that's 18. That's 1. Is there any way I can make 6 out of 18 and 1? No. So not that one. So I flip them. I'd have 2 and 9. Is there any way to make 6 out of 2 and 9? No. Okay, so we try something else. The only other option is 3 times 3, so I hope that works. That would be 6 and 3. Is there a way to make 9 out of 6 and 3? Yeah, what's the sign of both of them?
Positive.
Both positive. Okay, fabulous. So I'm going to get rid of these, and we're going to guess and check for the bottom. This one is set up normal. It's just x and x because there's no coefficient for the first term. What are the things that multiply to 15?
3, 5.
3, 5, and 1 and 15. We'll fast forward a little bit. If we have 3 and 5, what are the signs that would give me negative 2?
Plus 3.
Plus 3 and minus 5. That is just a factoring step, so if that's blurry to you, go find a video online that teaches you how to factor. Pretty sure I have them online, but you can also find anybody on the internet to teach you to factor within reason. Make sure it's a reputable source. After this, what happens? That's my hole. That's the hole in the graph. I'm left with 2x plus 3 over x minus 5. So we've done the first step. It said cancel out, get rid of the holes. Then all you have to do is set the denominator equal to 0. How do you solve for x here?
Plus 5.
Plus 5 on both sides. Easy peasy. So my vertical asymptote for this graph is at x equal to 5. And I'm done. We've done this before. We've just not seen it with the idea of calculus behind it. Because what this means for us, knowing that this is the vertical asymptote, which I'm not asking you to write the limit statements for your homework, but I just want to show you that the limit as x approaches 5 of f of x would be equal to positive or negative infinity. That's what calculus is telling me now that I know there's a vertical asymptote. That as we approach it, it's either going to go to positive or negative infinity, which means potentially the limit could or could not exist. Because if
So why do we not, so what about the numerator? Does that not matter?
that would give me the zeros of the function, it doesn't give me anything about the vertical asymptote. So I really don't care. Okay. What about the second one? The first thing we do to try to make sure we know where the holes are is we factor. Is there anything I have to factor in the numerator? Can I factor the denominator really quickly though? Yeah, it's x minus 3, x plus 3. Voila, these cancel. So I'm really just left with the function 1 over x plus 3, bless you. So what's my vertical asymptote? Because we set the denominator equal to 0 and solve for x, the vertical asymptote is just x equal to negative 3, which is the way we had done this problem before, but applying it to calculus, which again, I'm not making you write the limit statements here, but this is why it's in calculus. The limit as x is going to approach negative 3 for this function, oh, it's g of x, would be positive or negative infinity. If they're both the same infinity, then you would actually have a limit at this point. If they were opposite infinities, the limit does not exist, which is not what we're showing right now. We're just showing that there is a vertical asymptote there. Check. Does that feel familiar? We've done that before. Here's what also is going to feel familiar. Horizontal asymptotes. But applying it to calculus, we now have limits. A horizontal line, y equals b, is a horizontal asymptote of if one or both of the following limits exist. If the limit as x approaches infinity, which means look on the right side of the graph, is equal to some number, or if the limit as x approaches infinity on the left side of the graph is equal to some number. But we have really nice acronyms that we've been using all year to talk about the horizontal asymptotes. They're Bobo, Botan, and Betsy. What does Bobo stand for? If it's bigger on bottom, then the limit is, and the horizontal asymptote is also 0. If it is bigger on top, then the limit, the n actually stands for no horizontal asymptote because it's going to either positive or negative infinity. So you would say there are no horizontal asymptotes. That's where the n comes for, none. Because it's going up or down, not to a particular number. And then the last one, Betsy, if the degree is what on top and bottom? The same, so equal. That's what the E in Betsy stands for. The limit is the blank of the coefficients. What do you do with the coefficients? Divide them. So we're going to call it the quotient because that's the fancy name for the answer to a division problem. But if you're like, I'm not going to remember that, write the word divide underneath there. And it is as simple as it has been this whole time. We're not going to write the limit statements because we want the useful version of this of finding the different horizontal asymptotes. Plus, I made you write the limit statements when we learned this back in the day. So we're just going to decide if it's Bobo, Botan, or Betsy. Now, when we're talking about the degree, we're talking about the largest exponent on top and bottom. The largest exponent on top is 3. The largest exponent on bottom is 3. Is this Bobo, Botan, or Betsy? This is a Betsy. The bottom is equal to the top. And since it's a Betsy, we're talking about the degree, not the coefficient, the little numbers. 3 and 3. Since it is a Betsy, then we know that our horizontal asymptote just appears when y is equal to the coefficient of the top divided by the coefficient of the bottom. And what is 15 divided by 3? 5. So my horizontal asymptote is 5. Which means that the limit is also 5. Whatever number you get as the horizontal asymptote is the limit. In number 2, is that a Bobo, Botan, or Betsy? It is bigger on the bottom, which means, what is the equation for my horizontal asymptote? Ooh. 0. Bobo's the 0 one, which also means that the limit is 0. And number 3, Bobo, Botan, or Betsy? This is bottom because it's bigger on top. The top has a 5, the bottom has a 2. So it's a bottom, which means it does not have a horizontal asymptote. And that the limit would be either positive or negative infinity. And for this one, it's positive. My advice to you is when it's a bottom, graph it. Because it may be going up, it may be going down. Positive graphs are going to be going up and negative graphs are going to be going down. But if you're like not going to remember that, graph it and look on the sides where it's going. It's probably going up to infinity unless you have a negative graph.
How can you tell just by the equation?
There will be a negative in the very front because then it's an odd function or it's a negative function. Negative functions always go down. If they're even, they both go down. If they're odd, the right side, let me face you. This is positive, this is negative.
Okay.
This would be an odd function because 5 divided by 2 is 3, or 5 minus 2 is 3, so it would be an odd one. Positive, going opposite way. That's in behavior business. So the back of these notes should be semi-familiar because we've done that before. But finding the limits analytically is the main gist of today, so that's the front page.